Atomic models. According to Dalton theory, atom is indivisible and consists of positively and negatively charged particles. Different atomic models were proposed to explain the distribution of these charged particles in an atom. Thomson's model of an atom. After the discovery of electrons and protons, and discovery of natural spontaneous radioactivity in 1896, Sir J. Thomson proposed the first model of an atom in 1898. This model is known as J. Thomson's model, or plum pudding model, of an atom. He proposed that an atom has a spherical shape of radius approximately 10 raised to minus 10 meters, in which the positive charge is uniformly distributed. The electrons are embedded into it uniformly, so as to give the most stable electrostatic arrangement, as shown in the above figure. In this model, the atom is visualized as a pudding or cake of positive charge with raisins, electrons, embedded into it. This model is also called raisin pudding model or watermelon model. The mass of atom is assumed to be uniformly distributed over the atom. This model was able to explain the overall neutrality of the atom, but failed to explain origin of atomic spectrum and alpha particle scattering experiment. Discovery of radioactivity. A French physicist, Antoine Becquerel, in 1896, proved that atoms are divisible, with the help of his famous discovery of radioactivity. The radioactivity is the spontaneous decomposition of atoms of certain unstable elements, like radium, uranium, thorium, etc., into atoms of other elements, followed by emission of some smaller charged particles and neutral radiations. When these particles were tested for electrical charge, by passing through strong electric field, the behavior was classified into three types. 1. The positively charged particles were found to deflect from the path towards negative electrode. These positively charged particles were named as alpha particles. The mass of alpha particle was found to be approximately 4 AMU, and has a charge of +2 units. It was proved that positively charged alpha particle is the nucleus of helium atom. Hence, alpha particle is represented as helium-42 or alpha-42. 2. The second type of particle ejected from radioactive source was found to deflect towards positive plate. The extent of deflection was much more than the alpha particle. Hence these particles must be negatively charged, and the mass of these particles must be very small as compared to alpha particles. Rutherford's atomic model. Rutherford, in an attempt to verify various models of atom proposed by Dalton and Thompson, carried out alpha particle scattering experiments in 1909. radioactive source of alpha particle was placed in the cavity of lead block. The alpha particles emitted from this source were passed through lead slit system to give a fine beam of particles. This beam of particles was bombarded on a thin gold foil of thickness 100 nanometers. The gold foil was surrounded by fluorescent screen of ZNS. Wherever particles strike the screen, a tiny flash of light was produced at that point. It was observed that 1. Most of the alpha particles passed through the gold foil without deflection. 2. Some of the alpha particles, that is, out of about 8,000, one alpha particle was deflected through a small angle, less than 90 degrees. 3. A very few number of alpha particles, that is, out of about 30,000, one alpha particle was deflected by a large angle greater than 90 degrees. 4. A very few, that is, one alpha particle, out of 10 million alpha particles, was deflected through an angle of 180 degrees. Characteristics of Rutherford's atom. On the basis of these conclusions, Rutherford proposed his model of atom as follows. 1. An atom consists of the tiny positively charged nucleus at its center. Nucleus contains positively charged particles. Almost entire mass of an atom and positive charge is concentrated in the nucleus. 2. Number of negatively charged electrons equal to the number of positive charges on the nucleus revolve in various orbits around nucleus. Thus, Rutherford's model of an atom resembles the solar system, in which planets revolve around the sun. 3. The number of positively charged particles in an atom is exactly equal to the number of extranuclear electrons. So, the positive charge of nucleus is balanced by negative charge due to all revolving electrons. An atom is electrically neutral. 4. The electrons and nucleus are held together by electrostatic force of attraction. Drawbacks of Rutherford's atomic model. 1. According to Maxwell's theory of electromagnetic radiation, when a charged particle revolves, it gives out radiation and loses energy. An electron revolving around the nucleus should continuously emit radiation and lose energy. Due to this, the electron should come closer to the nucleus by following spiral path and ultimately fall into the nucleus. The time required for fall of electron into the nucleus is almost instantaneous, 10 raised to minus 10 seconds. Hence, atomic model proposed by Rutherford must be unstable. But in practice, this does not happen. 2. According to Rutherford's model of an atom, the electrons can occupy all the positions from the wall of the nucleus, 10 raised to minus 15 meter, to the size of atom, 10 raised to minus 10 meter. Atomic spectrum is related with the energy radiated by the revolving electrons. Electromagnetic radiations. Radiant energies, like microwave, radio waves, infrared, visible light, ultraviolet, X-rays, gamma rays, etc., possess sine wave nature. They are composed of electrical and magnetic components, in the form of waves oscillating at right angles to the direction of journey of radiation. All radiations travel at equal speed of 3 multiplied by 10 raised to minus 8 meter per second. This is also the speed of visible light. Different radiations have different frequencies and different wavelengths. Frequency V of radiation wave is the number of cycles of wave that pass a given point in a unit time. It is measured in the unit cycles per second. The SI unit for frequency is Hertz, denoted by Hz, and 1 Hertz equals 1 CPS. The wavelength is denoted by lambda. It is the distance between any two nearest identical points on the wave. It is measured in meters. Smaller unit is micrometer. μm equals 10 raised to minus 6 meters, or nanometer, and m equals 10 raised to minus 9 meters. The velocity, c, frequency v, and wavelength of electromagnetic radiation are related by equation v equals c upon lambda. The wave number, bar v, of electromagnetic radiation is also important characteristic. It is the number of waves in 1 centimeter path. It is related with wavelength as bar v equals 1 upon lambda. It is always measured in the unit per cm. Hence, v equals c into bar v, or bar v equals v upon c. Quantum theory of radiation. Heated matter emit energy. It was assumed that radiant energy was emitted by tiny oscillating, charged particles. The frequencies of oscillation of these particles are varying continuously with the variation of temperature. German physicist Max Planck, in 1900, stated that radiation neither absorbed nor emitted continually. The radiant energy is discontinuous and consists of small bundles of energy called quanta, or photons. That is, the radiant energy is quantized. According to Max Planck, the energy of a single photon is given by the equation E equals hv. That is, energy depends upon frequency of radiation. H is universal constant, called Planck's constant, and has value 6.6256 into 10 raised to 34 joules second. Atomic spectra. When a beam of radiation is dispersed into its component wavelengths, a spectrum is produced. A simplest device used for obtaining spectrum is a glass prism, which disperses white light into its components, consisting of 7 colors. Radiation of different wavelengths, ranging from 400 to 700 nanometer. Similar spectra can be obtained by using grating. A grating is made by scratching closely spaced parallel lines on a polished surface. If a substance or element is exposed to continuous electromagnetic radiation, certain part of radiation of corresponding wavelengths may be absorbed. This results into atomic absorption spectrum. It is discontinuous line spectrum and consists of dark lines on bright background. The excited species emit the energy absorbed in the form of atomic emission spectrum, which consists of bright lines on dark background. The discrete lines in absorption or emission spectrum support the quantum theory of radiation. Atomic spectrum of hydrogen. Swiss mathematician J. Balmer, in 1885, discovered a series of lines in the emission spectrum of hydrogen, invisible region. The series is known as Balmer series. He found that the wave numbers of all lines of Balmer series are given by equation bar V equals 1 upon lambda equals R square bracket 1 upon N1 square minus 1 upon N2 square bracket closed. The equation is known as Ritz combination principle. R is Rydberg constant and has the value of 109,677.58 per centimeter. For Balmer series, N1 equals 2 and N2 equals 3, 4, 5, 6, up to infinite. In infrared region, Pascal discovered another series in the spectrum of hydrogen. He also discovered that the lines in the Pascal series also obey equation 4, with N1 equals 3 and N2 equals 4, 5, 6, 7, finite. After the discovery of Balmer and Pascal series, another 3 series, Lyman bracket and Fund series, were discovered. Lines of all these series were found to be satisfactory equation, and astonishing, in case of all the lines of different series. The value of R was found to be instant, 109,677.58 per centimeter. Table gives the list of different series observed in hydrogen spectrum, along with the region and values of N1 and N2. Different series of hydrogen spectrum. Series Lyman N1 equals 1, N2 equals 2, 3, 4. Region Ultraviolet series Balmer N1 equals 2, N2 equals 3, 4, 5. Region Visible series Pascan N1 equals 3, N2 equals 4, 5, 6. Region Infrared series bracket N1 equals 4, N2 equals 5, 6, 7. Region Infrared series Fund N1 equals 5, N2 equals 6, 7, 8. Region Infrared. Ritz combination principle was totally based on experimental observations. No theoretical proof was given to the equation. Bohr's model of hydrogen explains successfully observations of hydrogen spectrum.